In this video I'm going to recap just a little bit on the GARCH estimation in Excel as suggested by Hull. So this technique is available from his website and from his book, and the GARCH estimation that Hull performed used S&P 500 data going from 2005 to 2010. He worked out the return, then the variance, and then he set out this log likelihood, which he summed and then optimized. So we performed the same exercise in Excel and we got the same sum of the log likelihood. We optimized using this setup and we found the same omega, alpha and beta estimate, and this is the specified GARCH 1.1 relationship that was outlined. So using the Volupta S&P 500 data, I performed the same exercise. So basically I ran through the same exercises here using the fab. The parameters now, the estimation however is somewhat different, because in the original Hull he estimates the return by taking the difference between the two cells and dividing by the previous. So the daily observation divided by the lagged daily observation was the return, and so on. And then the variance, the initialized variance value for using the Hull outline was just you initialize the variance by taking the square of the return, and then the next cell on, this relationship was mapped out by taking the omega, and then you took the alpha value, you squared the return, and then you took the beta estimate times the variance. In the following in line with an alternative specification consistent with GARCH that we looked at from the Volupta website that we estimated and got these parameter outputs. In this outline, we don't square the return, we take the variance of all the returns, and the return is not given as the change divided by the original, it's the log difference. So we take the ratio of these two, and then we take the natural logarithm of that, and that gives us a kind of exponential or continuously compounded return as opposed to a discrete return. And then we initialize the variance. So this relationship starts out, the first observation here is the variance, but then the second cell, if we double click, is again the same type of setup, but we use this cell here, which is the variance population, or the population variance of that column. So with the omega, we have the alpha times the return squared. The return is given here as the C3 by C3, so that's the return squared. And then we have beta times D3, and D3 is the variance here. Okay, now if I put in other values, so let's go 0.0 whatever 5, 0.8 and 0.7, something like this, and then go to data solver, and what we have here is, so we want to maximize this cell here. So E511 is this cell. Okay, just to make that clear, we want to maximize that cell by changing these values here, and then we solve, and the values we get are, okay, so these values here are the values that are optimized. we then multiply this value by 0.0001. The reason why we do that is because in the optimization we want to kind of give these equal weights so that no single parameter here swamps the others. And these parameters that we just optimized correspond very closely to the values that we got from Xcode. So if we look at this, there's 7.207, there's 0.9. So for the beta value here, 92101. So it's approximately, it is the same. The omega value is this value here. So if we put in 60, so it's the same value, 7.27. Okay, and then the value for the alpha, 0.7456, so we're approximately the same here, okay, on the estimation. So the two are consistent. The sum of the log likelihoods, just the sum, and remember what the steps were. To solve for that, we say this cell should be maximized, so maximize the log likelihood by changing the trial values, these values here, and we would have solved, and then they converged, and we got this set of values here. Okay, so that's the fab data, the Volupta GARCH model that we had estimated in using Xcode, C++ and Xcode, and we seem to get the same values.